I'm going to talk about something that I call dictionaries with implicit keys. It goes under various other names as well. Some people call it the retrieval problem. Some people call it storing a function. And kind of on this problem is related to something that Michael discussed yesterday, perfect hashing. I'm going to show you, in fact, a simple construction of a perfect hash function. The first one we'll see is static, but actually we can make it dynamic using signatures that we also saw before. And then towards the end, I'm going to talk a little bit about how to store a function or solve this retrieval problem without using perfect hashing. So what is the retrieval problem? So we have a set of items, and let's suppose they come from some field. If you like, think of them as numbers, and we are going to do operations modulo p. And what we want to do is associate with each element in the set some value also from the field. Say. Okay, so we could say that we represent a function f from S to the field. And you already saw something that can actually be used to solve this yesterday. So we saw that for any set of inputs, we can have any set of outputs, or any vector of outputs, if we take a suitable polynomial. Okay, so, and kind of the striking thing here is that if we think about the space for storing the polynomial, so that's just the coefficients, we need to store one coefficient per element in the set. So that's S times log field size bits, which basically means that we only store for the values. We don't store for the keys. In fact, just looking at it as polynomial, we have no way of knowing what is actually the set S. In some cases, actually, you may not want to store the keys themselves. So either because they use a lot of space, or because you somehow don't want to reveal the keys. Okay? If you know Shamir's secret sharing scheme, it's an example where you actually don't want to necessarily store the keys. Now, this of course requires the values that we store to be in this field from which the key comes. So what if it's actually something smaller that we want to store? Suppose we want to associate one bit with each key. Maybe we have a set of URLs, and we want to associate a single bit with each of these URLs. Can we actually do this without storing all the URLs? Well, maybe you can say yesterday we saw a way of shrinking stuff. So Mikkel was talking about how you can take some keys and map them down to much shorter things. But even if you do that, the keys are going to be relatively long, 64 or 128 bits or something like this. We would like to avoid this kind of overhead. Kind of the classical way in which people approach this is using perfect hashing. Okay, so we have this set, let's call the size n. And we can assume that we already mapped down. So each key is some constant times log n bits. And now we'd like to carefully choose a hash function that has no collisions among items in S, but also has a relatively small range. So let's call the range size R, where we are going to assume or aim for linear in n. So once we have such a function, it's very nice, right? Because we can simply take a hash table of size R, and when we see a key, we evaluate the hash value, and we know that it's only this key in this set that has this particular hash value. And here we can put whatever information we like, for example, a single bit. So if we can just find this perfect hash function, we can solve this retrieval problem. Then we give a little bit of motivation. So one piece of motivation is that we have very long keys and we want to associate just a single bit of information with them, but there are lots and lots of applications in data structures. So one of my favorite applications actually is the following. we want to know, is x approximately, okay, let me write it like this, in S. Okay, so by this I mean there exists some x prime where the Hamming distance to x is 1, say, and x prime is in S. Okay. So does x have Hamming distance 1 to something in S? So how do you solve this? Well, one thing we could do is to kind of generate all the vectors of Hamming distance 1 to x. So that would take time w, and we could look up each of them. So that's one solution. So that's easy. But now, suppose someone actually told us where the error is, so to speak, right? In which position is it that x differs from x prime? Suppose someone told us that. Then it was easy to verify. We would just flip that bit and then go look up the key. So now, what we need is just a function that maps S star. So S star is the set of bit strings that have distance at most 1 to something in S, and map it to 1 up to W. So we just want, for each possible query that has the answer yes, this function returns where is the error. And we can flip that bit and go look up the changed string. So if we can store this function in an efficient way, so this is a pretty big set, right? So it has size n times w. So we don't want to spend too many bits per key here, but such a value here only uses log w here. So in principle we could store this using not much more space than the set for the set itself.
But why don't you just store S star?
That would require nw words. And I would like to use less space. See?
But you're following Uri's question. Why are you saving the location 1 through W? If you know that something is an S star, you don't need to, I don't see why you need to actually know the location of the error.
It returns the location of the error if it is an X star, but it returns some number for anything that's not an X star.
Exactly.
So
Okay, so that's for verification.
Yeah, so this is important. So if we evaluate this function on something that is not in the set where it's defined, it will just return some value, but we will never know if it is in there or not. But in many applications, it doesn't matter, or we can check later on if the value we got was actually a value of something in the domain of the function.
Can you store a function from S star to S?
That I could also do, but then it would require log n bits rather than log w. Yeah?
So could you explain again how you store F efficiently?
How I store? Okay, so that was just motivation. So now comes the ways of storing F efficiently. So as I was saying, if we could have such a perfect hash function, that would do the trick, right? So we would just store the values in this case, numbers between 1 and w in the hash table, and that would be it. perfect hash functions are extremely rare. So if you read the Art of Computer Science, for example, Knut will say that these are so hard to find, right? But now, many years later, people have actually found ways of computing such things. But before we go to perfect hashing, I would like to talk about what you might call less than perfect hashing. So suppose that we are aiming to map to a range of size twice the number of items, and the hash function is just 2 independent. Then what we can do is count the number of collisions. Okay, so how many pairs of items do we have that collide? So it's just for each pair we have probability 1 over r, then it collides. And if we just bound the number of pairs by n squared over 2, we get a bound of n over 4. So we expect n over 4 collisions. So of course each collision there can be there are two keys. So there can be, we expect at most n over 2 keys to be involved in a collision. So this also means that conversely we expect at least n over 2 items that are not involved in a collision. So even a pretty weak hash function like 2 independent is actually going to have a lot of items for which it's perfect. So now the simple idea, which is actually, it only appeared in the last 10 years in the literature, for some reason, is simply to store hash values of S1, so these unique hash values, you store them as a bitmap, and then you recurse on the rest of the items. So it looks something like this. So we have this first function that hashes to a range of size 2n. Some of these hash values are going to be unique, so there we put a 1 bit. Other positions are going to be non-unique, there we put a 0. To evaluate this, right, I think the battery slide. Evaluate the perfect hash function. What we do is we compute the 2 independent hash function. We go and look up this first bit array. If we find a 1, we know that this was a unique value for this set, and we're done. So the hash value is just the position in this first array. Otherwise, if there's a 0, we go on to the next one and evaluate a second 2 independent hash function. If we find a 1 down here, we have a hash value. Well, somehow we need to concatenate all these ranges, right? So we're going to end up with a range of 4n, and that's actually also going to be the space. That is going to be the space usage. So we use 4n bits to store the information on when to stop, so to speak. So you evaluate these pairwise independent functions until the bitmap tells you, now you can stop, you have your unique values. And this adds up to 4n bits. Actually, if you choose these sizes a bit more cleverly and use slightly stronger hash functions, you can get down to something like e times n. And the number of levels is going to be logarithmic. So there are some keys that would require logarithmic time to actually compute the hash value. In fact, it's possible to improve this to log n, but I'm not going to do that now, even though it's relatively simple. But actually, if you think about it, the expected time to compute a hash value is constant. So So what happens if you want to compute a hash value of something that is in the set? Well, half of the time we are going to stop here, half of the remaining time we are going to stop here, and so on. So in expectation we need 2 steps. What if we evaluate something that is not in the set? Well, it's kind of the same thing. With probability, constant probability, we're going to stop in the first level here just because we happen to collide with some element in S. So the expected time to compute this is constant. There are other constructions of perfect hashing that has constant worst case. And somehow people concentrated on this, and this is maybe why this construction didn't appear until, I think, 5 or 10 years ago. Now suppose, so this is going to give us some holes in the hash table, right? So this is going to give us R equal to 4n. Suppose we want to actually map down to the minimal range, so just store a table of values. Then there's something called a rank data structure that is used a lot in succinct, so very space-efficient data structures that simply allows us to compress everything down. So basically it will, given that position here, it will tell us how many ones are there above. So that kind of allows us to compress this into a range of size n. So that was perfect hashing using 4 bits per key. So another trick we can do here is to add signatures. So instead of just storing a bit, saying that something hashed here, something unique hashed here, we can actually put a small signature that tells us something about what was it that hashed here. And suppose, for example, that we put a small signature of log n bits. So log n is going to be 6 or 8 or something like this. We can actually shrink the tables a little bit if we do this. So one thing this is going to give us is actually membership queries. So like Michael talked about yesterday, Bloom filters give us membership queries with some probability of false positive. So if you think about this data structure, what happens is that we go down until we find a signature of something that may be the key that you are looking up, or it could be some other key. Okay? But if you check against a signature of log n bits, for example, the probability that you have the same signature as whatever key is stored there is only going to be 1 over log n, unless, of course, you are searching for the key that is stored there. So using basically the same structure, just with signatures, we can get these approximate membership queries with small error probability. The space is going to be bigger than Bloom filters, but the time is going to be constant, independent of the error. Okay, so it's kind of a different trade-off. But the reason that I really showed this is that this actually works in a dynamic setting. Okay, so we can actually insert new things. Okay, suppose we want to insert a new key. What we do is we start at the top level. We find the place, the hash value of the key up there. Maybe there's a signature. In this case, we go on. Right? At least if the signature is different from the signature of the key that we are inserting. If there's no signature, we just insert the signature of the key. So the thing that can go wrong here is, so the goal is still to have perfect hashing. This thing that could go wrong is that we have the same hash value and the same signature. two things hashing to the same place. But it turns out to be not too bad, because this happens rarely enough. So this happens just with probability 1 over log n. So whenever this happens, we can actually afford to store just the key itself. So with probability 1 over log n, we store log n bits. Basically. So the total size here is going to be 2 log n plus O of n bits for a perfect hash function where you can insert new elements. And it turns out this is actually optimal. Okay. So in the dynamic case, you can really not hope to just get something that's linear, and then you actually need this log n factor. Okay, so that was all I wanted to say about perfect hashing.
So Rasmus, you can also delete elements, right? Just by bubbling up.
So, deletions is a bit tricky because we have no way of recomputing the hash values.
Oh, right.
Right, so we just have the signatures in there.
Oh.
So then you would have to store the key somewhere else, which is what most people do when they talk about dynamic perfect hashing. So they actually have the key stored somewhere and they can pull them out. But if we just think about forgetting entirely about the keys, this is the best you can do. And deletions is, well, tricky. So there's a lot of implementations of perfect hashing. So it's almost like a competitive sport. So people have been making better and better solutions. And the best ones use something like 2 to 3 bits per key. At least the implementable ones. So there are some theoretical ones that use less than 2, but I wouldn't want to implement them. But this is already pretty close to optimal. So it's possible to show that to store a perfect hash function, basically because they are so rare, they are exponentially rare in the number of elements, you need more than 1.44 bits per key. So there's no way we can hope to get below that. But of course, perfect hashing is just one way to solve this retrieval problem. So maybe there's a different way, another way of getting solving retrieval that gets rid of this fixed cost. So this is what I'm going to talk about next, and it's also kind of going to be a warm-up to Michael's lecture later on. That's going to use many of the same techniques. So we're going to use 2 hash functions. And whenever you have 2 hash functions, you can associate a graph with the hash values. Okay? So for a particular key, we associate an edge that connects a vertex given by one hash value to a vertex given by the other hash value. Okay. So the vertices are hash values and the edges are pairs of hash values. And let's just assume that one hash function maps to the range 1 up to r half, and the other one maps to r half up to r. Okay, but we draw the graph in this bipartite way. So now the idea here is to choose hash table entries such that to get a particular value, we just compute the hash values and we look up the corresponding entries and add them up. Okay, so does this work? Okay. So let's try on this graph. So suppose, for example, that we want to. So this edge here corresponds to an item, and suppose we want the value 8 associated with this. Well, then we just have to put 2 values that have a sum of 8. So we could choose 8 and 0, for example. And suppose these are the other values. Well, it turns out we can kind of start from one end. Maybe we put 0 at the top left. Now we are forced actually to put a 3 here, turn this forces this value here to be, let's see, 4. 4 plus 7 is 3. And you can kind of go on like this. And it works. Okay. So I'm sure that if I gave you 2.5 seconds, you could think of cases where it doesn't work. Okay. So what are conditions that make this work? Well, as this example kind of shows, if this graph is acyclic, if it doesn't have any cycles, this is going to work. You can just start somewhere and kind of greedily fill in these values, and it will work. So the question now really is this graph acyclic? And to answer these kind of questions, so we have a graph that is generated by a random hash function, we can go to random graph theory. Now this assumes that we actually have fully random hash functions. So let's assume that. So what random graph theory says is that basically the way this random graph is going to look depends on how many edges there are compared to the number of vertices. So in particular, if the number of edges is strictly less than half the number of vertices. So n is less than r divided by 2 plus epsilon, for some positive epsilon. Then we have something that looks like a bunch of trees. Well, at least almost. There is a probability that we have trees plus 1 edge. This is called a pseudo tree. It's going to look almost like a bunch of trees and be acyclic. And if we put in more edges, actually with high probability, we are going to have lots of cycles. Okay. It's actually possible to show also that it's going to be acyclic with constant probability. So if we are willing to choose hash functions a few times, eventually we are going to find ones that make this graph acyclic. And then everything works. Now, how good a solution does this give us? Well, we need n to be less, so the number of keys to be less than half the range. So in other words, the number of values we need to store is 2 times n. Okay. So it's still not quite as good as we could hope for. But we can look at it in a kind of a different way. Okay. So instead of looking at it as a graph, we can look at it as a matrix, which is kind of natural because we're really solving a linear system. So this matrix is going to have 1 row for each key x. So let's call that Vx. So that's this row. And this row is going to have almost only zeros, but we're going to have a couple of 1s. So 1 at position h1 of x, 1 at position h2 of x. So if you think about the process of choosing these values in the hash table, it's really solving a linear system involving this matrix. And now it's maybe more natural to generalize to more hash values. Okay? So instead of just using 2, we can use 3 or 4 or 5 hash values and hope that we can choose a smaller matrix. So one that's going to require a smaller vector to find a solution. And in fact, this works. Okay. So we just need this matrix to have full rank. You can also think of this as hypergraphs, but I find, many people find this difficult to think about. Acyclic hypergraphs, there are several definitions and so on. But there's this notion of peeling that you can always find something that is was associated only with 1 key. And it turns out that it actually helps if you have more hash functions. So for 2 hash functions, I claim that there we need r to be 2 times n. Okay, so the ratio between r and n is 2. If we go to 3 hash function, it drops significantly. So now it's around 23%, or less than 23% above the minimum we could hope for, which is 1. If we go to 4, it actually gets worse. Okay, and it kind of makes sense. It's the more ones we put into this matrix, the harder it's going to be to find an isolated one in one of the columns. So k equal to 3 is kind of the optimal choice for this. And this basically means that it's enough to store about 1.23 values per key to solve the retrieval problem. But actually, if we solve the linear system in a different way, so this was for repeatability. Okay, the question was?
If some of the values have 2 functions and some 3 functions, like the values between 2 and 3, could you go? Is the optimum exactly 3, or could you do better if some have 2 and some have 3?
Okay, so the question is, suppose that we sometimes have 2 hash values and sometimes have 3.
Mm-hmm.
It's possible to do better. In this case, and you can in fact, yeah. So this is a different route to actually achieving repeatability. As far as I understand, so this is related to some coding theory. As far as I can understand, it's actually possible also to approach an optimal solution in this way. The drawback being that some values will require a lot of hash functions. Okay. Even though on average they will require 3. Yeah, so that's a very good point. Alright, so we can make this ratio of the size of the data structure to the number of keys arbitrarily close to 1. So this basically means that we can have a solution to the retrieval problem which is arbitrarily close to the space you would just need for only the keys, only the values. But the drawback, if you want to go this route, is that solving the linear system becomes more demanding. And actually one of the possible ways to address this is exactly as you were suggesting, to use these non-regular hypergraphs that you get if you vary the number of values per key. But I think there's still more work to be done there. Alright, so if you want to read more about these things, some of these things are actually about, so the first paper here, for example, shows this log n number of levels, for example, that I claim. And there's a lot here that I didn't talk about, but in case you're interested in knowing more. So now the idea is to go to an exercise which kind of blends something that Michael talked about yesterday, these invertible Bloom lookup tables, with things I talked about today, which are these bipartite graphs that become acyclic. So the idea is to work out some more details and actually try to prove some of these things. So that's the plan for the next